Dear students, today we'll see the 13th section of our ECD lab, in which we are going to study what do we mean by a bridge rectifier, and then we are going to calculate its efficiency and ripple factor. And along with bridge rectifier, we will see what is a filter, what are filter components, and what is means how the C filter will work. So let's start with the topic. So the our topic will be bridge rectifier and filters. And in that we are going to see what is a full wave rectifier, what is how is the working of bridge full wave rectifier, what are the waveforms of full wave rectifier, efficiency and ripple factor of bridge rectifier, filter and filter components, working of C filter or capacitor filter, then advantages of bridge full wave rectifier, disadvantages of bridge full wave rectifier, and then applications of bridge full wave rectifier. Okay, so let's start with the a concept of full wave rectifier. Now, in our last class, we saw what was half wave rectifier, and with that we used one diode, and we saw that the half wave rectifier was working only when the input cycle was positive, and when the input cycle was negative, it was not conducting, it was going into reverse bias, so there was no output. That is what we studied in half wave rectifier. So if you see the waveforms of half wave rectifier, say this is your half wave rectifier waveforms. If the input you take it like this, input will be alternating quantity. Okay, so alternating a quantity, this is time. So for half wave rectifier, this is your input, say Vn. Okay, and then the output, whatever you see, will be existing only when the input was positive half cycle. There will be no output when the input is negative half cycle. Okay, so you see that when the input is positive half cycle, the diode, the single diode which you are going to use for your half wave rectifier, that will give you a output when the input is positive half cycle. When the input is negative half cycle, there is the diode is reverse bias and you will not get any output. Okay, so it will work only for half cycle. That is why it is called as half wave rectifier. What do we mean by half cycle? Now, one complete input cycle will be like this, in which you have one positive half cycle, one negative half cycle. So if the rectifier works for only half of the cycle, if it is giving output for only half of the cycle, then it becomes a half wave rectifier. If the rectifier gives output for both positive half cycle and negative half cycle, that is a full cycle, then it will be called as full wave rectifier. Okay, so if you see a full wave rectifier, then for full wave rectifier also, if you give the same type of input as you have given for half wave rectifier, okay, so this is the input, positive half cycle, negative half cycle, positive half cycle, negative half cycle. Okay, so this is the input, this is 0, this is time. Then if you see the output of full wave rectifier, then here you can see that the output, let the input be positive half cycle or let the input be negative half cycle, the output will be positive half cycles only. A unidirectional quantity you will get. The output will be in only one direction. So this will be the output, okay, for your full wave rectifier. This will be the output for full wave rectifier. So this is input for full wave rectifier, and this is output for full wave rectifier. Full wave rectifier. Okay. So if you see the definition on top, you can see that a rectifier circuit, okay, a rectifier circuit that rectifies both the positive and negative half cycles. Okay. Now, if it was half-wave rectifier, we would have told only one positive half cycle. But now we are speaking about both positive and negative half cycle. A rectifier circuit that rectifies both the positive and negative half cycles can be termed as full wave rectifier, as it rectifies the complete cycle. both positive and negative half cycle completely, it is going to rectify. For both the inputs, you are going to get the output in one direction. Okay, so that is your full wave rectifier. Then if you see the circuit of full wave rectifier, so here we have shown the circuit of full wave rectifier. So this is your circuit diagram of full wave rectifier circuit. Then here you see this is the input source. Okay, so this is the source, which is input source. This is input source, and the input is an alternating quantity. So here you can see this is an alternating quantity. Okay, so it will be having positive half cycle, negative half cycle, positive half cycle, negative half cycle. That alternating quantity is your input over here, whatever you have shown this symbol. Okay, now this input is connected to a bridge combination. So here you can see diode D1, D2, D3 and D4, which are connected in bridge. So this is your bridge. Okay, this is your bridge connection of diode. 4 diodes are used. And then you see that here terminal D is connected to the load resistor, and then load resistor is connected back to terminal C here, and the input is given to terminal A here, and negative the input is given to terminal B here. And here you are having your load resistance R1, and across the load you will be getting the voltage developed, which will be, this is your output voltage. Okay, now how does this circuit work? Now this circuit explanation we can give like, if the input is positive half cycle. Okay, so input is positive half cycle, say this is positive half cycle. When the input is positive half cycle, the current will flow from here and it will reach to this point A. Okay, so the current has started from here and it has reached point A. Okay, now it is a positive supply. Now positive supply, if you give to D1 diode, the cathode will become more positive than anode. It will be reverse bias, so it will not conduct. If you give to D2 diode, then the positive will be given to anode. Anode will be more positive than the cathode. This diode will conduct and there will be a current flow from here. Current flow from D2. Now this current will flow like this, and then it will flow across the resistance, and then it will come back to the returning path. Okay, from here it will come here to the point C. Now point C, it will make diode D3 work. Okay, the diode D3 anode will be positive with respect to cathode. Now D3 will work, and then that current will go back to the negative point of the source. Okay, that means it has started from here and it has ended here. Okay, now this is when the input was positive half cycle. So when the input was positive half cycle, okay, positive half cycle, then at that time the diodes which are conducted were D2, D2 and D3. Okay, whereas D1 and D4 were off. D1 and D4 were off. Similarly, when you see the input is negative half cycle, that time this side will be positive and this side will be negative. That time the current will flow from here, it will come to point B here, and at point B you can see diode D4 will be forward biased. Then the current will go from here, it will go from here, and here it will flow in the same direction as it had flown earlier for the positive half cycle. Then it will come back, return path will come here, it will come to point C here, then diode D1 will conduct and it will go return to this terminal. Okay, that means when the input is negative half cycle, when the input is negative half cycle, okay, half cycle, then diode D4 and D1 will work. D1 will work, they will be forward biased, whereas D2 and D3 will be reverse biased. Okay. Now in this way, what we will see is whether the input is positive half cycle or negative half cycle. Here at the load, you can see the current flows from top to bottom. In both the cases, it flows from top to bottom. That is, it is flowing in unidirectional. And that unidirectional current multiplied by this R resistance, that is, becomes voltage. V is equal to I into R. And that voltage will be a unidirectional voltage. So here you can see a unidirectional voltage. Let the input be positive or negative. The output voltage will be positive half cycle only. So that is what we say the alternating quantity by the source what we gave here. This was AC. What we gave here is converted into a unidirectional output which is DC. Okay. So this is how your bridge rectifier is going to work. It is basically going to convert alternating quantity, alternating current into direct quantity, that is direct current. And in this, we are going to use a bridge circuit which consists of four diodes D1, D2, D3, D4 at a given time, at a given input of positive half cycle or negative half cycle. Two of these four diodes will conduct, and they will see that the current flows in the same direction for both the cases across the resistor. Means through the R resistor, load R resistor, the current is going to flow in same direction. Then if you go to see the note on working, then it says that in the first positive half cycle of the AC signal, the diodes D2 and D3 become forward bias and start conducting. That is what we have seen. At the same time, diodes D1 and D4 will be reverse biased and will not conduct. Okay. The current flow through the load resistor via the two forward bias diodes. The voltage seen at the output will be positive at terminal D and negative at terminal C. That is what we have seen in the circuit. Now, during the negative half cycle as input of the AC signal, the diode D1 and D4 will be forward biased and diodes D2 and D3 will become reverse biased. The positive voltage will appear on the anode of D4 and negative voltage will be applied to the cathode of D1. It is worth noting that at this point, the current that will be flowing through the load resistor will have the same direction. This is important. Same direction as it has with the positive half cycle. Therefore, no matter the polarity of the input signal, the output polarity will always be the same. We can also say that the negative half cycle of the AC signal has been inverted and is appearing as a positive voltage at the output. So let the input be positive half cycle or negative half cycle, the output will be a positive half cycle only at the output of the rectifier. Then the same circuit, if you see in a practical mode, then in practical mode, your AC, which you take from the AC mains, should be first given to a transformer. So this is the AC voltage, what you're going to take from the AC mains, and AC mains will be your 230 volt 50 hertz. Okay. Now this is your AC mains, what you're going to give here. And now we don't require 230 volt, okay, 230 volt for our electronics applications. So we will step down that voltage with a transformer. So this is a transformer with primary and secondary coils. Okay, and this will step down the voltage. So here whatever voltage you will get will be lesser voltage. Say it can be 10 volt or 20 volt or so. Okay, but that would also be a alternating quantity only. Alternating quantity is converted into alternating quantity only, but only the voltage level, the magnitude of the voltage has been brought down. Okay. Now this alternating quantity you are going to apply to this circuit. So again, when the input is positive half cycle, you can see that here this diode will work, and then the current will flow like this. Okay. The current is going to flow like this through the resistor R, and here you can see it is going to flow like this, and then it will come here, it will go through D3, it will go to the point here, negative path, returning path here. Okay, similarly when the input is negative half cycle, this is going to come here, and then D2 will work, then the current will be flowing like this, same, it will come here, it will go through D4 and it will go back to the above side. So at the load resistor, you will see that the current is flowing in only one direction. So the voltage developed across the resistance will be in one direction only, and you will get a voltage supply like this. in one direction only at the output. Okay, so this will be the output of your bridge rectifier when the input is alternating quantity. Now, if you see the waveforms of the bridge rectifier separately, then you can see here that on top we have shown the sinusoidal input signal. So this is your sinusoidal input signal. That means it is an alternating quantity input. So you will be having a positive half cycle, negative half cycle, positive half cycle, and negative half cycle. So when the input is positive half cycle, you are having a output which is a positive half cycle only. When the input is negative half cycle also, you are having an output which is positive half cycle only. Again, when the input is positive half cycle, you are having an output which is positive half cycle. And again, when the input is negative half cycle, you are having the output which is positive half cycle. So this output is in one direction only. So we say that your AC alternating quantity is converted into one direction, unidirectional, that is direct quantity. Okay, so alternating current is converted into direct current. Clear? This is the waveform representation of your bridge rectifier. Then again, we have shown the same thing here. You can see the same type of waveform here. The input is your AC input, and the AC input is given as your positive half cycle, negative half cycle, positive half cycle, negative half cycle, positive half cycle. And for every half cycle of the input, the output will remain in one direction, that is positive half cycles only. Positive half cycles only. Now, this type of DC, what you get from this AC, now this is your AC and this is your DC. Now, this type of DC, because it is having some AC component in it, this type of DC will be called as pulsating DC. So here you have named it as a pulsating DC. So this is your pulsating DC. This is not your pure DC. And this will be the output of your full wave bridge rectifier. Then we want to see the efficiency of full wave rectifier. So whenever we speak about efficiency, it will be a relation of output upon input. It will be the ratio of output upon input. So here, if you see about rectifier, if you have a block diagram of a rectifier, so if you see rectifier, the output of rectifier will be DC and input of rectifier will be AC. So here you will be having AC power and output will be DC power. So here you will be having PAC, AC power, and here you'll be having PDC, that is DC power. So if you take the ratio of PDC upon PAC, then it will give efficiency. Efficiency will be denoted by this letter, and it is equal to PDC upon PAC. Okay, so here you can see that efficiency is PDC upon PAC. Okay, that is DC output power upon AC input power. Clear? So a rectifier efficiency is defined as the ratio of the DC output power to the AC input power, and it is given as PDC upon PAC. Then how to calculate that efficiency for full wave rectifier? So for full wave rectifier, the average current, which is called as IDC, okay, the average current is given as 2Im by pi. So here you can see this is where you have given the average current IDC is equal to 2 into the maximum current upon pi, where pi value will be 3.14, or you can take it as 22 by 7 approximately. Okay. Similarly, the root mean square current IRMS is given as Im by root 2. So here you can see IRMS is given as Im by root 2, that is maximum current upon root 2. Okay. Now we are going to take the efficiency formula. Rectifier efficiency is given as DC power PDC upon PAC. So here, now here we will take power as current square multiplied by resistance. Current square multiplied by resistance. So power can be given as current square multiplied by resistance. It can be given as voltage square upon a resistance, or it can be given as voltage into current. Okay, these three formulas are there. Now from this we will take the first formula, P is equal to I square R. For PDC, this I will be IDC, and for PAC, this I will be IRMS. So we will get this formula here, I square DC RL upon I square RMS RF plus RL. So here we are considering the forward resistance of diode also along with the load resistance. Okay. Now if you substitute IDC and IRMS in terms of IM, then you will get 4 Im square upon pi square into RL here upon Im square upon root 2 square into RF plus RL. So here we have shown this. Then if you again simplify that, you will get 4 Im square upon pi square into RL into root 2 square upon Im square RF plus RL. Again, if you simplify that, you will get this 8 upon pi square into RL upon RF plus RL. Then again, if you simplify that pi square, if you take it as 3.14, so 3.14 into 3.14 will be 9.85. So you will get this simplification 8 upon 9.85 into RL upon RF plus RL. That if you again simplify, you will get 0.812 into RL upon RF plus RL. Then you will get it as 0.812 upon RF plus RL upon RL, and then this you will get it as 0.812 upon 1 plus RF upon RL. Okay, now because RF is very small value, okay, the denominator will be taken as negligible. Okay, so here if you see in this equation, that is 0.812 upon 1 plus RF upon RL, there, if the diode resistance RF is negligible as compared to RL, then the above equation 0.812 multiplied by 100 will give the percentage of efficiency. And here we see that the efficiency of a full wave rectifier is given as 81.2%. Efficiency is given as 81.2%. So here you can write efficiency of full wave rectifier is 81.2%. This is what you have to remember. This is what you have to remember for full wave rectifier. Then what is ripple factor? Okay, so generally the meaning of ripple factor is the output of rectifier will not be a pure DC, it will be a pulsating DC. Pulsating or DC means a DC which is having some AC components. The AC component present in the output of rectifier is called as ripple. Okay, so for that we will find out what is ripple factor. So here if you see the definition, the rectifier output mainly includes the AC component as well as the DC component. The ripple can be defined as the AC component within the resolved output. Okay, now if you want to derive the expression for ripple factor, and if you want to find the value for full wave rectifier ripple factor, then we will see that according to the definition of ripple factor, the whole load current RMS value can be given as this whole load current RMS. You can see in this first equation, I RMS is equal to under root square of I square DC plus I square AC. So this is your first equation. Okay, then or you can write the same equation as IAC is equal to under root square I square RMS plus I square DC. This will be second. When the above equation is divided by IDC, then we get the following equations. This is your third equation where you get IAC upon IDC is equal to 1 upon IDC square of I square RMS plus I square DC. This will be your third equation. However, here IAC and IDC is the ripple factor formula. So ripple factor formula will be 1 upon IDC under root square I square RMS plus I square DC. So that is given as this. This is the formula of ripple factor. So this is the formula for ripple factor. What you have to take now, this can be written exactly like this. This is under root. This is under root. Okay. Now here you are having I RMS upon IDC. This is whole square minus 1. This is the formula for ripple factor for a rectifier. Now what is IRMS and IDC for full wave rectifier? That will substitute and we'll find out what is the ripple factor. So for full wave rectifier, we know that IRMS is equal to Im by root 2 and IDC is equal to Im by pi. Okay, so we know the formula for ripple factor, that is IRMS upon IDC whole square minus 1. If you substitute this IRMS and IDC in terms of Im in the formula for ripple factor, then you will get this values here. So our ripple factor is equal to under root of this expression here, and this expression, if you substitute with their values of pi and im will get are cancelled out, then here output you will get as 0.48. So ripple factor of full wave rectifier is 0.48. Okay, this also you have to remember. Ripple factor of full wave rectifier is 0.48. Then the next, after knowing what is bridge rectifier, we will go to see what is filter and water filter components. Now this will come into picture because the output of rectifier is a pulsating DC. It is not a pure DC. Now if you want to convert pulsating DC into pure DC, then you have to use a filter. Okay, so here we'll see the definition. The filter is an electronic device that allows DC components and blocks AC components to the rectifier output. That means at the rectifier output load, only DC should reach. AC should not reach. Okay. So the filter is made up of combination of components such as capacitors, resistors, and inductors. Now, a capacitors, if you see, according to their reactance, that is opposition to the flow of current, capacitors will allow the AC component and blocks the DC component. Whereas if you see, depending upon the reactance of inductor, the inductor is one which allows the DC component and blocks the AC component. This is proven because you know that the reactance, that is opposition to the flow of current, for inductance and a capacitance is given as this. For a capacitance, the reactance, that is opposition to the flow of current, is given as 1 upon 2 pi FL. Okay, so it is reactance is inversely proportional to frequency F. And for inductor, the reactance is given as 2 pi FL. So reactance is directly proportional to frequency F. That is why a capacitor will allow AC and block DC. An inductor will allow DC and block AC. So whenever you want a pure DC to reach to the load, you always connect a capacitor parallel to the load and an inductor in series with the load. Okay, that is what a filtering action you will get. Clear? So here if you see the work of a capacitor filter, we are using only a capacitor filter at the output of rectifier. So here you are having your output of rectifier which is pulsating DC. So here you will having pulsating DC which will look like this, pulsating DC. Okay, now that will be your input. Now once that input is put here, the AC component of that pulsating DC will pass through this capacitor and go to the ground. So it will go to this ground and only the DC will pass ahead and will reach the load. Okay, that means the output here, okay, instead of having like this, okay, instead of having like this, the a capacitor will charge and discharge. Okay, whenever it is positive half cycle, it is going to charge and discharge, charge and discharge, charge and discharge. Okay, so you'll get an output like this, and this output will take it as a pure DC, whereas this earlier output of the rectifier was pulsating DC. Now, this is what is the use of the filter components like a capacitor or inductor. So here we have seen a C filter, capacitor filter, and that is been connected across the load. If you are having an inductor, it will be connected in series with the load. Okay. So here you can see the circuit and also the capacitor filter. So here you can see your full wave bridge circuit, and in that full wave bridge circuit, so this is your input source, input AC. Okay, and here you are having a bridge circuit D1, D2, D3, D4. Here you are having your load resistor R1, and after the load you are having filter capacitor C1. Okay, so this will be the input, that is the alternating quantity, plus minus plus minus. The output will be pulsating DC for the rectifier. This is your pulsating DC, and after you put the a capacitor, after you put the a capacitor, you will get only this output: charging, discharging, charging, discharging, charging, discharging. So that will be purest form of DC, whatever is possible with the capacitor filter. Okay, so here you can see this is the rectified ripple, whatever you got first. This was your pulsating DC. This is what you're shown in a dotted lines. This is your pulsating DC. Okay, and then when you put a capacitor, you get only so much. That will be you're reaching towards a pure DC. Actually, a pure DC should be a straight line, but this is practically you're going near to pure DC. So here, how does the a capacitor work as a filter? So for that, you can see this note. This output voltage of single polarity is not pure DC voltage, as it is pulsating and not a straight line in nature. This problem is quickly solved by connecting a capacitor in parallel with the load resistor as shown in the figure. In this new design, the positive half cycle will charge and a capacitor via the diode D2 and D3, and during the negative half cycle the a capacitor will stop charging and will begin discharge itself through the load resistor. This process is known as filtration, and a capacitor acts as a filter. A capacitor has improved the pulsating nature of the output voltage, and it will now only have ripples. This waveform shape is now much closer to a pure DC voltage waveform. The waveform can be further improved by using other types of filters such as LC filter, where L, that is inductor, will be in series and a capacitor will be in parallel with the load. Or you can have a pi filter where you can have a parallel arc capacitor, then a series inductor, again a parallel arc capacitor, which can shape like a pi shape. Okay. Then we'll see what are the advantages of bridge rectifier. So it is very obvious the advantages of bridge rectifier as compared to your half wave rectifier. It will be having number one, low ripples in the output DC signal. Number two, high rectifier efficiency. And number three, low power loss. Similarly, if you go to see the disadvantages of bridge rectifier, number one is bridge rectifier circuit looks very complex. And number two, more power loss as compared to center tap full wave rectifier. Now here I want to explain you that the full wave rectifier are of two types. One is center tap full wave rectifier and one is bridge rectifier, what we have studied now. So as compared to center tap full wave rectifier, this bridge rectifier is having more power losses. Okay. Then if you go to see the applications of bridge rectifier, then number one, for supplying a polarized and steady DC voltage in welding application. Number two, inside the power supplies it is used. Number three, inside battery or chargers it is used. Then number four, inside wind or turbines it is used. And number five, to detect the amplitude of modulating signals. And number six, for a conversion of high AC to low DC voltage also it can use. And it has many other applications also. Here are few applications what we have named. Okay. Thank you, students.